Great, so we're looking at number 3 from 3-6, and we're asked to determine whether the vectors in this given set S, if they can span the whole vector space. And so thinking about span, the question that you might ask is, in this problem, using just those 4 vectors that were given, can I write any point in 3 dimensions, right? So R3 is sort of our 3-dimensional space, and S is this. So there's a handful of ways you might think about this. Let's sort of write some of those out. One way you might think about this is, for an arbitrary ABC, can I write these by adding up the other vectors and multiplying them by some numbers? So could this be C1 times that first plus C2 times this next one plus C3 times the last one, or the middle, second last one, the penultimate, plus C4 times 0, 0, 1. So that's one way of thinking about this problem, is can I write any arbitrary ABC in this way? And so if you were to do it in this method, you would then maybe write this out as A is equal to C1 plus 2C2 minus 5C3. The C4 is multiplied by 0. B is equal to, notice everything there is 0. Then C is equal to negative C1 plus 4 C2 plus 2C3 plus C4. Okay, so in this problem, it looks like, yeah, you could probably, by picking arbitrary C1, 2, 3, and 4, you can get A and C to be whatever the heck you want, but B is stuck. You cannot write most numbers, right? So if B was 3, you couldn't get to that space. And so if this were sort of a 3-dimensional point, I think about in 3D with your X, your Y, and your Z. This would be like saying you'd be stuck in the XZ plane because your middle value, your Y value, could never be off the 0. So you'd be stuck somewhere in this plane. So it doesn't span all of 3D space. There are some of the ways that you could do set the same problem. If you don't like sort of reasoning it out in this method, recall in this section we could talk about turning these vectors into a matrix, and then we could talk about the column space. Right, so we could talk about, say, the matrix 1, 0, negative 1, 2, 0, 4, negative 5, 0, 2, 0, 0, 1. So turn it into a matrix. We could multiply it by some vector x, but in this case, your vector x, you might just call it C1, C2, C3, C4. And this is going to be equal to some arbitrary vector. You can call it vector b, or for our purposes, you might call it A, B, C. Notice, I can see this being a question. You have a vector with 4 components on the left and a vector with 3 on the right. But recall, after the matrix multiplication, since this A has 4 columns and 3 rows, so rows by columns is 3 by 4. And this is 4 by 1. After the multiplication on the left-hand side, you end up with a 3 by 1 space there. 3 by 1 vector, I should say. So then the question is this, or the way it's defined in your book, is there at least one solution for really any vector b here? And so this vector b. And sometimes there's a solution, right? So there are some vectors that you can write this way after multiplication. But what you would maybe notice here is that you can find a counter example. Not all vectors can be written this way. In fact, after you do the multiplication, you're going to have a vector whose components are exactly what we had up here. And you would recognize like that's not going to be an arbitrary vector. So that's sort of two ways of thinking about that same problem, and they're very close. They often come down to a little bit to something like a notational difference. All right, so now in number 4, we're not considering the space of real numbers. Right? We're not doing R3, but the space of here are polynomials, right? And so the P with a little 2 down there, that refers to polynomials of degree 2. It could be less, but not more. So in this case, we're going to ask, do these 3 functions span that? Or, in other words, could I write an arbitrary secondary polynomial by adding these 3 different functions together in different ways, right? So what we want to know is if these span, then I should be able to write any second degree polynomial where a, b, and c are real numbers. They could be 0. Can I write this as, for any a, b, and c, sum c1 times 1 plus some constant times t plus 1. Let me sort of scoot over a little bit. I might just put it down over here. Plus some constant c3 times t squared minus 2t plus 3. So I need to say for any a, b, c you give me, I better be able to write them in terms of c1, c2, c3. So what I could do for this problem, if I want to avoid matrices and stuff like that, I could just multiply things out and group them. So if I were to multiply the right-hand side, I'd have c1 right, plus c2 times t plus c2 plus c3 times t squared minus 2c3 times t plus 3c3. Okay, so let's group this in this way. So we have c3 times t squared. Maybe do it color-wise. So everything that has a t I would also group. So I have a c2 with a t, and then I also have a minus 2 c3, both those multiplied by a t. And then just the constants by themselves, I have c1 plus c2 plus 3c3. And then the question is for an arbitrary ABC, correct these out. Well, A would then have to be c3. B would have to be c2 minus 2c3. And the last c would have to be c1 plus c2 plus 3c3. So if I can do this, then I would be set. And so what I could then go ahead and look for is, well, solving this like a system of equations, and I can definitely get this to reduce. And so because I can write any value of a, b, c in this way, I'll be able to say that this does in fact span the vector space of polynomials of a degree 2 or less. So that's one way you could look at this problem, and you might want to just work this out just to make sure. The way you might visualize this is that notice how this top one is just C3, so those are just going to be whatever it is, right? So if A is 2, C3 is 2. Now B would have to subtract off some stuff from A, but this C2 is a free variable, so it could be whatever the heck you want. So then I can get B just by choosing C2 at will. Then for this last constant, well, C2 and C3 are already taken because they determined A and B, but then I have this other free variable C1 in there. And because of that, you can sort of eyeball and say this will be solvable. This will give me a solution where I can get all these different values uniquely. That's one way of doing it. Another way you might look at it is as follows. This is maybe the next sort of level of thinking, but here we have, in the second degree polynomials, we have constants, which is sort of 0th degree, 1st degree, and then 2nd degree. Right, so we have 3 of them. And what we can ask then is, well, we have 3 vectors, or 3 functions here. You might think of them as sort of 1 by 1 vector. And because the second degree polynomial is sort of, it sounds kind of weird, but it's a 3-dimensional space, if these 3 are linearly independent, then they will span P2. So let's check if they're linearly independent. So I'm going to come up here. So in order to check if these are linearly independent, I'm going to go ahead and call this first F1, F2, and F3. So I'm just going to come over here. Maybe I'll zoom out so we can see it while I still have some space. So what I'm going to go ahead and do is check the Wronskian. So the Wronskian of this, F1, F2, F3, is the determinant of the matrix that has those across the top. So 1, t plus 1, and t squared minus 2t plus 3. Then the next row are the derivatives, so 0, 1, 2t minus 2, 0, 0, 2. Now we can just move over here so we can just look at this Wronskian. So here's our Wronskian. So to take this determinant, I'm going to go ahead and look at the 1 in the top left corner, and then expand going down, so I really don't have to worry about the first one. So it would be 1 times the determinant of the smaller matrix, 2t minus 2, which gives you just down to 2. So the Wronskian's determinant is 2. Now think about that theorem we have for Wronskians. So if there's at any point, if there is any point that your Wronskian is non-zero, then those functions are linearly independent. And this is always non-zero, right? This is 2. 2 is never equal to 0. And so that tells you these are linearly independent. And so they will span our space here. But again, that's requires recognizing that it takes 3 vectors, so 3 functions, to span P2.